Welcome back to The Explainer. Today, we're targeting a highly specific and, honestly, highly frustrating challenge in the Cambridge AS and A-Level Mathematics exam. Specifically, we're looking at Syllabus Section 6.5. We're going to completely deconstruct hypothesis tests and show you exactly how the examiners are grading Type 1 and Type 2 errors behind the scenes. Look, most students bleed easy marks here. It happens all the time. But by the time we finish up today, you absolutely won't be one of them. We're going to crack the code on this one.
Okay, so let's dive right into this massive challenge. Why on earth do students continuously drop easy, guaranteed method marks when they're running these complex, multi-stage hypothesis tests? It's literally happening year after year. Well, we're going to look at the exact data pulled directly from the principal examiner reports, debug these incredibly common errors, and figure out exactly how to fix your execution so you can secure maximum points on exam day.
We're going to treat these exam questions like a strict logical algorithm today. We'll walk systematically through our 4 modules: core principles, the exact procedural framework, critical analysis, and finally, those top examiner warnings. Let's get into it.
Starting with Section 1, Core Principles.
Right off the bat, Cambridge explicitly lays out their benchmark for top-performing candidates. Mastery requires systematic analysis and evidence-based reasoning over superficial breadth. They don't just want a broad, shallow understanding, they want analytical depth. What this really means is you have to understand the actual core logic of hypothesis testing. You need to know that a Type 1 error is, essentially, rejecting a true-null hypothesis, like a false positive. And a Type 2 error? That's failing to reject a false one. But it's not enough to just memorize that. You need to understand this logic deeply enough to seamlessly apply it to completely unfamiliar, abstract context when they throw a curveball at you. Moving right along to Section 2, our procedural framework. Think of this next part as your core execution code. Whenever you tackle a hypothesis question, you must run this strict 5-step loop. Step 1, deconstruct the question. Step 2, extract only the relevant data from the texts and tables. Step 3, select your precise analytical framework. Step 4, execute your calculations using crystal clear notation. And Step 5, present your final answer using the exact correct terminology. This is your algorithm. If you skip a step or rush the syntax, your response fails to compile and you lose the points. It's really that simple.
Now, the absolutely crucial point here is what we call the method mark strategy. In the Cambridge system, examiners are actively looking to award you points just for following that exact 5-step sequence we just looked at. They are grading your logical process, not just the final number. Think about that for a second. Even if you make a minor, silly arithmetic slip somewhere in Step 4, if your procedural framework is solid, you will still capture the vast majority of the marks. They want to see your logic. Process is quite literally everything. All right, Section 3, Critical Analysis. Let's level up.
So to clear that basic descriptive level and push into the evaluative tier, which by the way is exactly where the highest marks live, you have to upgrade your output. You literally have to prove higher order thinking. You must evaluate alternative interpretations. You need to compare different approaches using hard evidence. And finally, you must draw justified recommendations based entirely on your statistical findings. Listen, it's just not enough to find a number at the end of your equation. You have to explicitly explain what that number actually dictates in the real world.
This right here brilliantly illustrates how top-tier students operate. They assess the quality of their evidence with absolute precision. They clearly and explicitly distinguish between identifying the limitations of their given data and identifying the assumptions they had to make before drawing conclusions about a Type 1 or Type 2 error. Critically analyzing your own mathematical logic and exposing your own assumptions is exactly the kind of high-level routine that examiners love to reward. Finally, Section 4. Examiner warnings. This is the ultimate debugging session.
This specific examiner alert reveals a massive, system-wide vulnerability in how students are writing their exams. The principal examiner report states, quote, "Candidates consistently confuse key terminology," end quote. Guys, students are bleeding points left and right because they just throw around terms like Type 1 error and Type 2 error without actually proving to the examiner that they know what they mean. The patch for this bug is so simple. Always define your terms explicitly before you use them in an extended response. Don't ever assume the examiner knows that you know it. You have to prove it on the page. Now, drilling even deeper into the historical exam data, the examiners have isolated 3 specific recurring errors. These are the bugs that repeatedly cause students to fail the assessment framework entirely. Let's map exactly what these are so you can completely bypass them.
First up,
Students disastrously confuse cause and effect when interpreting the results of their hypotheses tests. It just scrambles the whole logic. Second, they completely ignore standard presentation formats, which means losing those easy professional skills marks we talked about earlier. And third, and honestly, this is a huge one, they provide these vague, generic, textbook-style answers instead of actually contextualizing their conclusions to the specific problem they were just solving.
If you truly want to optimize your exam strategy and clear the examiner's firewall, you absolutely must prioritize application over abstraction. You have to ensure that every single conclusion you write down is tied strictly and explicitly to the distinct scenario provided in the prompt. For example, if the exam question is about a factory manufacturing light bulbs, your final conclusion about a Type 2 error better specifically mention the actual real-world consequence for those light bulbs. Don't just paste in a generic statistical definition. Lock it into the context.
All right, let's review our final, high-scoring cheat sheet architecture. To summarize the explainer today, first, always deploy that 5-step procedural framework so you can secure your method marks, even if your math slips. Second, patch that memory leak by explicitly defining your terminology before you use it. Prove you know the definitions. And third, rigidly anchor your final conclusions directly to the prompt's real-world context.
As you boot up your preparation for the upcoming Mathematics 9709 exams, I really want to leave you with this final diagnostic question. When you sit down to run your next past paper, are you treating your hypothesis tests like a frantic, hopeful guess, or are you treating them like a precise, airtight, examiner-approved algorithm? The choice is entirely up to you. Thanks for joining us, and we'll see you in the next explainer.